I'm going to talk a bit today about anonymity, traffic analysis, privacy, the whole bag. Hopefully you've been coming to a couple of the sessions in this track already, and I won't have to go over all of that since that's it's a 2-day seminar. I'm going to assume you know enough about cryptography to know what it's good for and what it's not good for, and I'm going to assume you know just a little bit less about traffic analysis. I'll go over that briefly. Anyone who has any questions at any point, just please raise your hand. I may, after hearing your question, tell you to wait till the end, but if something's not clear, just stick your hand up and wave, and if I don't see you, yell at me. So, back in the beginning, we had the ARPANET, and people didn't really care about things like passwords and security and all that, because everybody trusted each other, and it was this academic military combination pet project that wasn't being really used for anything that was privacy critical. There were some forward-thinking papers at the time. They followed on the heels of the invention of public key cryptography, one of which, probably the most important of which even today, was David Chaum's paper in 1981 about that first proposed mixes, which essentially described a way of using public key cryptography to create nested messages that could be sent from Alice to Bob through a chain of independent operators who each had a key that the messages were sequentially encrypted to, so that you might have 5 remailers in a chain. They all publish their keys. Alice takes her message, she encrypts it, possibly encrypting it to Bob so that the last node can't read, possibly not, but encrypts it to the last node, and then encrypts that blob to the second to last node, and on back toward the node that she's going to send her message to, and that's a mix. She sends her message to that one. Other people presumably are sending their messages to that as well. The messages get put in there, sorted around like a hat, and pulled out in different order, and sent out along the way, so that the first node gets to see that Alice is sending something, doesn't know where the message is going to, though, and the last node gets to see that Bob's receiving something, doesn't know where the message is coming from, unless he's smart and realizes that Bob is always the receiver of messages in cryptography and Alice is always the sender, but likely that's not how the real world works. So, the initial concepts behind mixes and a number of the initial possible attacks and some brief mentions of how to fix them were in this paper that David Chaum wrote. It was a fairly short paper, and it's got a whole lot of material in there, but basically it was a seminal paper that opened the door to a whole field. And during the 1980s, there was not that much work done on it. With the exception of a group of people, some of them at IBM Zurich, some of them at a number of German universities, that were publishing improvements, attacks, advances, alternate methods of doing these sorts of things. You could look up Andreas Fitzman's work. Unfortunately, most of this was unknown to the rest of academia outside of German-speaking regions, because they published everything in German, and furthermore, they put it in Word files. Thankfully these days, thankfully from my English-speaking only perspective, things are published in English and printed in PDFs, and I don't have to worry about word viruses. But in the 80s, they didn't have to worry about them, so I'm not knocking them for that. Americans during that time were, with the exception of a handful of papers, pretty much apparently either oblivious or uninterested in the field of mixes and the field of anonymity in general. There was a lot of focus on various types of cryptography, advancements in block ciphers, stream ciphers, public key cryptography, etc. But the whole mixed field wasn't considered serious. Toward the late 90s, after a group of hobbyists in the Bay Area called the Cypherpunks started actually implementing these things from 1980, 1981, the academic community started to get more interest in this, and in starting with a workshop called PET, Privacy Enhancing Technologies Workshop, this became a legitimate thing to study in academia. And now I don't have an exact count. I was trying to figure it out earlier of the number of papers written. But if you check out the Freehaven Anon-bib, there's a list where if you were to plot the number of papers published over time, you see a huge spike during the early years of this decade, and particularly the last 3 years. I'm going to take a little digression here and briefly touch on what's going to be inevitably somebody's question, why do you need anonymity? Again, hopefully these reasons are at least understood. If you don't agree with them, at least you understand them. But people are generally accustomed to being able to speak in private and not have to worry about eavesdropping, unless they're in an occupation where they have to bug sweep their homes, in which case they're hopefully doing that. But back in the day, you could go out into a field and chat with somebody about the possible merger of your two crop companies or whatever, and be pretty well guaranteed that nobody else is listening in. The internet changes that. Now, the internet has made it is an incredibly powerful tool that makes it very easy for people who may never actually meet each other in person, may never be able to meet each other in person, maybe because they can't leave their country because it has restrictions on travel or simply practicality. The latency of messages has gone from waiting until the Pony Express brings your mail to whoever you're sending it to a mere matter of seconds if you're running a decent mail server. But unfortunately, the internet makes it almost trivial for eavesdroppers of many different classes of capability to listen indiscriminately to all kinds of communications going through. And if you were at the traffic analysis panel, how many people here were at the traffic analysis panel? So I know how much to go over again. Okay. Well, since most of you weren't, there's this concept called traffic analysis that simply focuses on watching who is sending messages to whom, and furthermore, sometimes what various features of those messages are. So a subset of that is known as the SSL fingerprinting attacks, where you can be doing everything over an encrypted session, but if there's no padding on the communication, people can have a dictionary of, okay, I load CNN, and it loads and it's going to be this size encrypted, and it loads these other objects, some of them are images, and they're going to be that size. And then furthermore, there's this decision tree of link paths that a user can follow. And if he follows them, he's going to get pages of this size, and you can use that to correlate to what they're doing. There's network analysis, where people are sending messages to each other, and if you want to find out, if two companies are considering an acquisition, you watch their lawyers, and suddenly there's lots of chatter between the two there. Or if you want to figure out who is at the hub of some sort of central social thing, social network, you can watch who the senders and receivers are and figure out who's getting a message after this other person sends something, or who's the person that everyone's sending messages to, etc. So in addition to being able to eavesdrop and actually observe the communication, applying cryptography to it, using PGP, using other possible encryption protocols, doesn't simply solve the problem, because quite often what's interesting to an eavesdropper or to an adversary isn't what's being said, but that it is being said, and of course who it's being said to. So that's what we try to solve with anonymity. We try to make it so that people can, first of all, send messages such that third parties can't tell who they are, and then in some cases allow two parties to communicate where neither party knows who the real identity of the other person, but they can be assured that they're actually talking to the person that they've been talking to this person. They don't know his real name, but he goes by the name of B0B, and they want to be sure that they're talking to the same Leet Speak Bob that they've been talking to for the last year. So there's systems that address that problem. Now, well, why do you really care? I have nothing to hide. I'm not all that interesting. These are all things I hear when I talk about this to my neighbors back home and my grandmother. Some of you just don't like the idea of creepy sysadmins reading your love letters that you're sending on their systems. And that's a perfectly reasonable reason to want to have protection. I think that people shouldn't have to have their love letters read by creepy sysadmins. I don't know. No offense against creepy sysadmins. I was one once, but I didn't read anybody's love letters. Then there's actual serious reasons. Whistleblowing is one of them. I'm not going to name all of them. I gave a talk with Roger, who just spoke, Black Hat 2003, where we talked about attacking and defending anonymity. The slides are up on the net. You can hunt that down and go through it. It goes into these details a lot more heavily. But what it all comes down to really is just a simple exercise of your natural right to privacy. People have had for up until this century, pretty much, an assumption that they could communicate and they could gather together, they could form associations, they could speak without fear of reprisal, and these are things that are being threatened by the powerful nature of the internet. And as I said, it's not the internet that is bad, it's the lack of protection against these new threats that the internet introduces. So, I'm not going to make this a philosophy talk. If you guys want to talk about philosophy afterward during the Q&A, you can raise your hands. I might not answer your questions simply because these are things that we all should be thinking about. Everyone that's involved in this democracy of ours, and threats to anonymity, threats to privacy, threats to people's freedom of speech, threats to people's freedom of association. These are things that you all ought to be taking seriously. I'm not going to tell you what you should conclude, but you should all think about them. Now, under the assumption that you think that they are important things, we're going to talk about some of the ways to actually make them happen and some of the problems with doing so. So as I mentioned before, the idea of mixes pretty much sat on the shelf for about a decade until during the 1990s when there was a lot of, if you know your crypto history, a big hullabaloo over whether or not cryptography would be legal in the United States unless there was a backdoor in it. And luckily, from my perspective, the good guys won and demonstrated that backdoored cryptography was not simply a cat's already out of the bag, you can't do anything about it problem, but also a very hard technical solution. The NSA, which is probably this country's single most concentrated employer of really smart mathematicians, came up with an algorithm for doing secure message encryption that had backdoors in it that judges could, when they all agreed was necessary, use to break messages, got their cipher wrong. So it's really hard to build secure things. It's really hard to build them so that they break when you want and not when you don't want. That's coming up again now in anonymity, and I'll get to that later. So, on the history front, some of the cypherpunks read Chom's paper on mixes and decided to implement it using PGP as the encryption layer. And unfortunately, there were dozens of problems that came up with the implementation as a result of that, and it's pretty much completely broken. It gives you a good warm fuzzy feeling that you have to go through all this extra work in order to send your messages, but it doesn't really buy you anything. There's no padding, there's the traffic analysis attacks are trivial against it, and yeah, it's, as I say, worse than the TSA security program. But unfortunately, I actually think the TSA security program really is just designed for the appearance of security, and the cypherpunk system was designed to provide real security. So that's, in some respect, a bigger problem. Unfortunately, despite it being so broken and everyone knowing that it's so broken, it's still in use today. So we'd like to see that change. In 1995, a cypherpunk known as Lance, and his name is Lance Control. He's now the president of Anonymizer, which some of you may have heard of. It's a single-hop passive SSL encrypted proxy. wrote Mixmaster, which tried to address a lot of the problems in cypherpunk remailers and tried to adhere more strictly to Chom's initial proposal. So it did a number of things, such as pad the messages to a fixed length so that each individual packet being sent wasn't distinguishable from other packets. Now, he had no system in there for rate limiting different packets. If you sent a message that was too large to be split into multiple different packets, or too large to fit into one packet, it would be split into multiple different packets, and then that would get sent. So if you wanted to send a big photo of your dog's fornicating or whatever, you'd probably have to break it into 20 packets, and you'd stand out from the rest of the crowd because, again, traffic analysis, you could analyze that most people are sending, there's a normal message sending pattern, and then there's what you're doing, which is big burst of 10 packets all at once. But the one key problem that, let's see here, the biggest problem with the cypherpunk mixes was, aside from the fundamental lack of a threat model being defined prior to implementing this stuff, was that they had inherently in the design replay attacks. And that's where somebody can take a message, one of these middle mixes can take a message and send it to the system again and then watch who gets the same, who gets an output again. And they can do statistical correlation there. The reason this was necessary in the cypherpunk mixes was to support NIM servers based on what's known as reply blocks, where essentially you have a mixed message that includes routing information that is associated with a pseudonym managed by that NIM server. And when somebody sends mail to that pseudonym on that NIM server, the NIM server encrypts it in a proper cypherpunk mix format and tacks on the routing information headers and sends it back through the mixes with the encryption on the routing information headers being peeled off so that the final mix knows who to deliver it to. These reply blocks were designed to be used over and over and over again. So that inherently means you need to have packets be able to be replayed. Mixmaster addresses this problem by keeping checksums of the messages that the remailers have processed and trashing ones that match. So you stop your replays, but you can't use the same sort of reply block-based NIM server system that the cypherpunk systems used, because you'd get one use out of it, and then that would be that. Oh, I jumped ahead here. One other problem with Mixmaster, it's still being used today, and it's still the dominant remailer, even though there are known problems with it. But fundamentally, the biggest problem with Mixmaster was that it's a Unix tool. It comes out of the box, compiles, gives you an ncurses interface, and you got a Unix shell, and who here uses Pine or Mud or Elm as their primary mail clients? So, all right, your target users for Mixmaster, you have no problem. The rest of you are going to go, why can't this plug into Exchange or Outlook, or why can't it plug into Thunderbird? And there's no reason why it couldn't, except for the lack of an elegant API. You're asking for software written in 1995 to interoperate well with GUI applications that really came to dominance in the late 90s, early 2000s, and that's kind of hard. Particularly, even though it's still being actively developed, it would require a major refactoring of the code. So there are a couple wrappers or Windows GUI systems designed to make use of Mixmaster. Jack Be Nimble, Quicksilver are a couple of them, but they are buggy, some of them unmaintained, and yeah, there's not a heavy emphasis on usability, and that's a problem. Mixminion. During there were discussions simultaneously between the members of the Mixmaster development team going, okay, how do we fix our problems, and how do we kill cypherpunk remailers because they're so broken? The reason they were still around is because they provided this reply block capability, the ability to actually pseudonymously receive messages. And there was a group of folks, two of whom are the active developers on Tor, that were independently working on solving these things. And what we ended up having was a Chaumian mix-based system that essentially behaved very similar to Mixmaster, fixed a couple of tagging attack problems in Mixmaster where you could flip a bit and the message would still go through the network and you could see that there was an error at the end and then do correlation between that and the message you flipped a bit on. But for the most part, it's Mixmaster, but with the novel idea of using single-use reply blocks, where the NIM servers keep a cache of reply blocks that get used for one message being sent and then are discarded. Unfortunately, is 5 years old, correct, Nick? What's that? Yeah, it's almost 5 years old, and it's still in beta, right? So there was this thing called Tor that came up and took all of Nick's time away, and yeah, one of the critical problems with being an open source project is relying on having lack of programmer redundancy. Mixmaster had a problem where our main Windows programmer was hiking up a mountain and fell off of it, and since then we've had really crappy Windows support because the guy that knew what he was doing is unfortunately no longer with us. But that was in poor taste. Pardon me here while I fix my microphone. Can you all hear me still? Okay, so despite Mixminion being better than Mixmaster and being almost half a decade old, it's still not being used for actual production use. I believe it has a disclaimer still in all messages going through, or that it shouldn't be used for anything real, or maybe that's just when you install it. But because of that, Mixmaster is still the most widely used Dreammailer software out there, and it generally does its job pretty well, with the exception of not having reply capabilities. Now, you might ask, well, what about web browsing? One of the big things about Tor is it can do web browsing. These mixes I'm talking about here, and also the systems that I'm going to describe going forward, are all for high latency applications. If you're sending email, you can wait half an hour for it to get delivered and generally not have a problem. In fact, back in the day, many of us had to do that just because of how slow things were. But I've seen Mixmaster used successfully for, obviously, email and Usenet postings, but also for anonymous blog publishing, where it does, you don't care if your blog is updated like that. It might take 45 minutes for the update to actually get through, but that's okay. But who wants to go and browse porn over a system where every packet takes about half an hour to get through? It's just, it wouldn't work. So solutions were needed. Enter the low latency mixes. We've had a bunch of them over the years. They've paraded through and all pretty much hit the floor and died, except for Tor. There was the Zero Knowledge Freedom System, which was technologically at the time very advanced, but unfortunately was done as a business, and they found that the cost of paying people to operate nodes and paying for that bandwidth didn't allow them to actually make any money when people started downloading their porn. Porn is the big use of the internet, so the fact that it's the big use of anonymity systems shouldn't surprise anyone. But yeah, things like web browsing, instant messaging, that sort of thing are the primary uses today of low latency mixes. They're designed to be usable first and foremost. And then the threat model is defined around that criteria. Now, that isn't a bad thing, because usability itself is a security consideration. In general, if you've got, like, say you have an email encryption program like PGP, if it's slow and clunky and confusing and takes a 45-minute crash course in crypto to actually get started using, a good portion of your users aren't going to use it, and therefore you've failed utterly because you're not protecting them. The early versions of PGP were actually kind of like that. These days, PGP is extremely usable and has addressed those problems. But an anonymity system that doesn't let you browse things in a reasonable amount of time isn't going to be usable, and people are going to turn it off. People are going to find ways to circumvent it, and that's just going to mean that you don't have users, and if those are users that ought to be using your system because they have real reason to be using it, you've just completely failed. It's just as though you had a system that was broken. The problem with the low latency mixes is there's this little thing called information theory and traffic analysis. And yeah, if I could find a picture of Claude Shannon with his middle finger up, I would have put it here. But Tor and the like are all pretty much trivially breakable by an adversary that can watch the network and perform rudimentary traffic analysis. Furthermore, some of the things built on Tor, like hidden servers, have had a number of papers come out that break them, using things like the clock skew on your CPU and packet latency and so forth. So, despite that, there's a definite need for Tor. It fills the gap for people that need to be able to use some level of anonymity system for low latency purposes. Unfortunately, there's good research and then there's unnecessary research. And there are a lot of clever papers on breaking Tor coming out, and then there are a lot of papers that are all based on the premise that Tor has a higher threat model than it does. And they pretty much say, okay, if we take Tor and we apply this more stringent threat model to it with a more powerful adversary, we can break it this way and that way and that way, and then they get that published. And unfortunately, that's not really all that useful to people like Roger and Nick, because they already know those attacks can happen, and they've said we're not protecting against them. This, if you want to write this down, this here is a repository that has most of the papers being written about privacy and anonymity, specifically anonymity, that are influencing the field today, or have influenced it by virtue of being some of the first written on the topic. But all your Tor attacks are going to be pretty much starting 2004. And there's a large percentage of papers written on anonymity these days that are simply focused on breaking Tor in ways that it's not supposed to be used in the first place. There's other threats to low latency systems. Systems like JAP, which they've finally renamed it after 7 years or so because they got sick of offending multiple ethnic groups. And they call it John Doe in unspellable fashion, but they rely on a concept called a cascade mix. Now, that's slightly different than the traditional mix, where you basically have, in the traditional mix model, a network that's unstructured and users pick their routes. In a cascade mix, either the entire route or sections of the routes are fixed. This server always sends to that server, always sends to that server. There's problems with that. Technical problems that can be solved, but one of the big ones is operators just can't decide, hey, I'm going to throw up a John Doe server today and just put it online and have it work. They've got to coordinate with the registration system to figure out how do they fit in, where do they fit in the cascade, and so forth. And this specific service has all of its, at least the last time I checked, which was several years ago, so don't hold me to this, but has all of its servers running within Germany. There's a paper written by Roger Dingeldine and one of his co-authors, whose name I'm blanking, but it's in the Anon bib, on why location diversity is important, both from a geographical and a network topology perspective. If you have a breach of the backbone and all of your nodes are on that backbone, you've got a problem. If you have suddenly an oppressive regime take over in a country. I mean, that couldn't happen in Germany, but in some of the more volatile countries, it's a real problem to worry about. You want to make sure that you have nodes outside of that jurisdiction so that operators can't either be replaced by people who are going to be stooges of the dictatorial government or be told it's the gun to your head or the keys to the remailer. But in systems like this, central control is inevitable. And a further note about the JAP system, they've already backdoored it once. They were asked nicely by the German police to please insert a backdoor to watch for traffic coming from a certain, either coming or going to a certain, I forget which, a certain IP address, and they complied. And one of them was a smart ass and put in the comments of the code, which were publicly available. Backdoor code section begins here, and luckily it was discovered within a couple days, but they've lost a lot of respect of a lot of people, including myself, as far as their willingness to actually stand up to threats to the whole purpose of their system, which is to provide anonymity. If they will comply with requests and not court orders, then they don't have the spleen necessary to operate these things. You've got a problem here. I mentioned the legal side of this, but also the hacking side. Any system that relies on a trusted component, this includes the anonymizer, which is a single hop, one-hop proxy, and if you trust everyone that works in an anonymizer, you still have to worry about their systems being compromised by an outside person, or there being a political situation such that they are forced by a court order to turn over their data. And sometimes, if any of you have done any, are actually aware of how the subpoena systems work, sometimes they aren't as narrow as they ought to be. And so suppose there's a legitimate reason for somebody like the anonymizer to be subpoenaed for one of their users' identities, but the subpoena is broader than that and says, give us your database. They have to comply. And all the innocent users get outed along with the bad guy. Back in time on a history lesson here, there was a service being run by Jolfo in Finland called Anon-Pennant-Fi. It was the first and probably to date the most successful anonymous email solution. It was simply register your pseudonym here. We have a mapping between your real email address and your anonymous email address, and you can give out your Anon-Pennant-Fi address, anon123@Anon-Pennant-Fi, and people can mail to that, and we'll just route back out to you. Of course, this doesn't resist against somebody watching the network and watching inputs and outputs, but it also didn't resist against hacking attacks. I've heard lots of rumors that people still have the database of the mappings, but the Church of Scientology decided they didn't like some stuff that was being published through Anon-Pennant-Fi and got the Finnish courts to subpoena the identities of a couple of the users there, and it was after that the operator decided that he would shut it down rather than keep operating it and keep putting his users at risk. So whether it's out of control judges or prosecutors or hackers breaking into the system, either way, you really have to make sure that you don't have any single component of your system built such that if it's compromised, it compromises the entire system. But back to low latency here. The approach I've been taking on my research here, and a number of people working on this as well, have been to keep working on improving Tor and similar systems because there's a need for that sort of solution. And if the threat model can't be as high as we like, okay, let's see how we can take where it is now and find ways to improve it without damaging its utility. And then on the other side, work on entirely new designs, develop stronger systems that protect against more advanced adversaries or adversaries that can see a greater part of the network or have greater computation power, etc. And the easiest way to do this is in the low latency systems, because our system constraint, our engineering problems are all much easier there. If I have the time to make sure that the number of users using the system is large enough to actually obscure the identity of people in it, then I can worry about solving some of the other problems. And one thing about anonymity, there's this concept called the anonymity set. That's the number of people in the network behaving indistinguishably from yourself. And that can be applied to the term of just a snapshot of now and also over time. I'll talk about this later, but there's an attack called a long-term intersection attack, where you pretty much take a snapshot of the anonymity set and watch people's behaviors and partition them into different anonymity sets if you can. But then you take further snapshots, and you try to correlate users between the two snapshots and then see where the partition sections differ. And then you can narrow in on your targets. So that's one of the problems that having a lower latency system actually helps with, because the lower your latency, the larger you can make your anonymity set if you address additional problems with that. But generally, there's a correlation between the two. And so as you get more users, you have the ability to worry a little bit less about, do we have a viable anonymity set right now to actually provide enough defense against the cover traffic, or against the traffic analysis. And there's the reply block system. So we thought we had something good with the mixed minion single-use reply blocks, but we don't. You can't use reply blocks. If you're working on them right now, give up. It's due to the intersection attack problem I had. They fail. Nick actually ran some simulations on what the performance and resistance to these long-term intersection attacks would be for a typical user who receives something like 3,000 messages a month, which, remember, on the NIM server front, it's an email address. It's out there on the net. Spammers send to it. And this doesn't matter if it's real messages or just junk email or mail that the attacker is flooding the NIM with. But we didn't consider that. We just considered real email and spam. About after a month's worth of incoming email, you can partition down the users such that you know whose NIM matches to whose real, to their real IP or their real email if it's forwarding that way. So there doesn't seem to be very much of a future for reply blocks. If somebody wants to prove me wrong and unfuck them, go right ahead. But I'm looking elsewhere for solutions. So in 2002, Bram Cohen and I sat back and thought, okay, we need a better solution to this here. This was actually before we had met Nick and Matthew and George and heard about the single-use reply block system. But we thought, all right, let's break the problem of sending and receiving email down into two discrete chunks. We've got the sending side pretty much well done with Mixmaster, Mixminion. What can we do to handle the problem of retrieving email anonymously? It was not until we independently reinvented an algorithm from the seminal PIR paper that we realized there was this field out there called private information retrieval. And once we did that, we were very happy that other people had actually done the work that we were worrying about, and we could worry about implementation. But the way PIR works, essentially, there's, as with any field, it's branched into different subsections. I'm going to be mainly talking about distributed trust, information theoretic, private information retrieval. Now, the distributed trust part, if you were here for Roger's talk, you understand. Basically, the way that works is you trust that the whole system isn't compromised. Individual components can be, but if the whole system is compromised, you lose. And the information theoretic part of it means that we're relying on mathematics that allows us to be secure against an adversary who has potentially unbounded computation abilities. So not only are we secure against governments and their the Chinese intelligence agency and their RSA cracking stuff, but we're secure against the aliens who can crack a million-bit RSA. Basically, throw more computing power at information theoretic secure systems, and you still don't win. We take Claude Shannon's work and we use that to our advantage. PIR also is a subset of oblivious transfer, generally, if that means anything to anyone here. And for the first 5 or 6 years that it was being investigated in the academic community, it was pretty much a solution in search of a problem. A lot of the introductions to the papers talk about how this might be useful for data protection in healthcare or other such central databases. I was very surprised at the time to realize that no one had considered using this for the basis of an email pseudonym system, but it was great because now I'm a PhD student and I need papers, so there was one for me to write. So, yes, the twofold approach. We use Mixminion to send the email anonymously. We'd be using Mixmaster right now because Mixminion doesn't currently have an active developer. Yeah, I covered that already. Covered most of this. I tend to do that. I get ahead of myself on my slides. But the core thing here is a lesson we learned from Mixmaster, from our mistakes. We've got to make sure this thing is usable. And when it comes to privacy or security, you're all aware, if you're here, that people don't want to install the newest security thing because it's cool, or they don't get excited about the newest version of this privacy protecting software. They have a secondary need for it. They want to send their email, or they want to browse the web. And what you're doing is addressing a problem that, if this were a perfect world, wouldn't need addressing in the first place. So, to that end, we need to make sure that our system is as invisible as possible to them. And when it has to be visible to them, is user-friendly. So I'll talk briefly about how we address those issues. The name of the proposed system we have is the Pynchon Gate. We named it after one of my favorite authors, who's a very privacy-conscious writer, Thomas Pynchon. Bram Cohen and I came up with the initial design. Nick came in, helped with a subsection of the paper with the analysis section about the reply blocks and general publishability issues, and he's been the author of the actual implementation spec, and he's advising Brian Warner, who's our main programmer. It uses a simple XOR PIR scheme that's an information theoretic PIR scheme, and it's distributed trust, as I said. Now, that doesn't mean that a single server can't bring down the system, make it unusable. It simply means that anonymity can't be compromised by a single system, or a single server. So our threat model here is we have an active attacker. And if you want more details about what kind of threat models are out there and what these terms mean and what other, I'll define these terms, but what other possibilities there are, again, I refer you to the talk that Roger and I gave at Black Hat 2003. But our attacker is an active one. He can do things like manipulate the messages that, he can put new messages in the system. He can try to manipulate the messages that are coming out of the system. He can potentially knock nodes off the network, and so forth. He's also a global observer, or might be, in that he can watch the entire network in real time and has the processing capability to actually do something about that, actually analyze his stuff in real time. This would obviously not be a real-time reading of all messages going through the system, but would more likely be a traffic analysis approach where the entire network was analyzed and statistical correlation of who's talking to whom is the main goal. And then we have the problem of rogue operators that we attempt to address, where our system is an open distributed trust system. Anyone could come and set up a certain component that I'll mention later. We have to consider that some of those operators might be malicious, might be the enemy, simply because if not, we end up falling back on the registration approach, where operators are vetted by some authority, and then that authority is trusted and could be coerced into putting the bad guys in, or furthermore, just simply can't prove to you that everyone who's doing this is honest. I liked Roger's T-shirt, which says something to the effect of, "I might be a federal agent." You've got to consider that. You have to consider, and particularly the people that are 6 degrees removed away from me have to consider that I might be a bad guy, and the operators that I'm appointing might be bad guys. So we need to have this open so anybody can come in and set up their stuff. And once we do that, since I'm not going to know everybody that comes in and sets up their stuff, and it's good that I don't because of other esoteric attacks related to that on the social front, I'm not going to trust the people that are running it, so I have to trust my system to still work even if they aren't trustworthy. So I'm going to try to go through the architecture here of this fairly quickly because I'm running out of time, I think. I don't know. But the architecture for the Pynchon gate is here. We have a forward network-facing component called the NIM server. That's what has your email addresses or has your IM names or what have you. We're building it for email, but it can be extended out to other things. It's designed to work on the internet 20 years from now, where the dominant communication method might not be SMTP. That, in turn, passes things to the collator, which in practice is probably going to be operating on the same server as the NIM server. We're building them on separate components because the code is cleaner there, and that allows for, if the network load gets to be too large for a single box operating both things, an operator just split it out to two things. But there's one operator, essentially, or one entity running this. And they're trusted to make sure the stuff is running. They can denial of service the entire network by taking it down. But they're not trusted to preserve the anonymity of the system. But the NIM server gets the incoming mail. And actually, I may have gotten this wrong when I wrote up my slides. I believe that what I'm saying here actually happens at the NIM server step. But messages come in, they're encrypted to a user's key, and passed to the collator, and they're put into the messages are organized into a 3-level hash tree structure, where the bottom level is a series of buckets. And messages fill buckets, and when buckets are full, they go to more buckets. Each bucket is a fixed size, and the number of buckets on the system is known and published. The collator, once it's finished processing a day's worth of messages coming in, closes the book on that day, pushes out that database that it has to multiple distributors. Now, these are the things that make this a distributed trust system. These are the components that the user ends up speaking directly to, and these are the components that, if all of them are working together, if all the ones the user is querying are working together, the user loses. But if one of them is honest and the rest are malicious, each time the user queries, the user is safe. So here's our diagram. We have senders sending their email to the NIMs. If a user needs to actually send control messages to configure their system, etc., they do it through a remailer, so it goes through the mixednet system. Or if a user wants to anonymously send something to a user of the Pynchon gate, they can do so. We we're plugged in directly with the mixed median transport protocol, so we don't have to use SMTP there. NIM server does its stuff, passes the encrypted email to the collator, which organizes everything into its buckets again, hands everything out to distributors. We're going to be using BitTorrent, something like it, to distribute the load there, because this is a perfect application for BitTorrent. It's a whole bunch of users that simultaneously want identical data of a very large size. So, and of course, there's checksums on everything. There's checksums on the full database, so each distributor can make sure it got a real copy, etc. And then we have the user here. This is labeled recipient, but really it's the Pynchon client. The user doesn't actually need to see or interact with any of this. But this sends what we call the PIR queries, the private information retrieval queries, to a selected subset of the distributors and gets its responses, reconstructs it, and gets its email. So a little bit more about how the NIM server handles the encryption here. We want to greedily encrypt everything. Basically, if a NIM server is broken into by a hacker, or seized by a thief, or subpoenaed and seized by nice police, we basically want to make sure that there's not collateral damage in the case of the police for people that aren't actually their targets or doing anything bad, et cetera. So in the case of the hacker, we want to make sure that everybody's protected and so forth. So we have two keys here. We have the long-term public key, which is what the user uses to authenticate himself and to encrypt his administrative commands that he's sending to the mixnet. And the short-term messages, which are what are used to send messages, or to encrypt messages that go from the NIM server out to the collator, out to the distributors. And those change. Here's a little bit of pseudocode, a little bit of math, where we actually describe I'm describing the system we have for rotating our keys. But the idea here is to have a deterministic system where you can derive tomorrow's keys, but you can't go backward. So the collator only has to hang on to yesterday, the day before's keys, and so forth, as long as is necessary. Which turns out there's a window where we have to assume that the user may be wanting to retrieve messages from a few days before, but once those keys become obsolete, they get thrown out. So if somebody compromises this and they learn these keys, they can learn all the keys going forward, but they can't then go back and decrypt all the stuff they've been watching on the network in the past. There's also each bucket has individual users' mail in it and needs to be identified in some way. We don't want to just have their pseudonym as the identifier there, because that could potentially leak information. So we have a forward secure, pseudonymous, unlinkable identifier that changes each time. So that's how we do that there. Ask me questions about that later if you're curious. The three-level hash tree I mentioned, the collator does, consists of the meta index, which is an index of the index buckets, which are an index of the buckets that contain the messages. The premise here is that you can the client goes and gets today's tree index, and then can use that to verify the hash of his message bucket by following it up the tree. And that protects you from having some tampering being done by a rogue distributor, possibly tagging your messages, possibly replacing them with something else, etc., to use the user as an oracle so that you can watch and see their behavior and learn something from that, and so on. This is a way to let the user verify that the answers that he got, the messages he got, were indeed untampered with. These are the same. This is the same bucket that the collator passed off to the distributors long ago. And this works. There's a problem with it, but it does what it is designed to do as far as protect you from these attacks. Other things we've done here that are a little controversial, but they work in the low latency system. Each NIM gets a fixed number of messages a day. When you set up with your your account, you specify. You're told the range and what the average number of buckets a person receives every day is, and you pick a number in that range, and that has a message capacity. So if you're expecting X number of messages a day, you want to pick a value there that can a value of number of buckets there that can actually accommodate that number of incoming messages, isn't wildly different from what everybody else is doing, and allows you to handle days where you'll get spikes of more mail than normal, but still is within your bandwidth capability. We understand that people aren't psychic and aren't going to be able to know what their future capacity is. So there's a whole system in place in there where if you can't fit all of today's messages in the number of buckets that are allocated, they get saved behind for the next cycle. And I talk about this in the later slides, so I'll get to that then. But if you end up getting less messages than or a few messages than you're expecting, you just end up with more padding in the buckets. You get the same number of buckets, and when they go through this PIR protocol operation, they come out looking completely random. So there's no difference there. This is vastly different than the reply-back-based system, where if you get lots of mail one day, you get lots of encrypted blobs coming to the real you that day. If you get nothing that day, then you get nothing coming to you that day. Here, everything is designed to work at a fixed size and a fixed number of queries, and furthermore, each person is within the parameter of being able to pick where on the number of buckets scale they want to fall, designed to behave pretty much like everybody else. We're trying to maximize the anonymity set and, if possible, have all users be part of the same anonymity set. All the distributors, as I said, are mutually untrusted, but due to the nature of this PIR protocol, we only need one per query to be honest, in order to preserve the user's anonymity. So the client is designed to work as a proxy or a network shim, where you point your email client at it, and you would do a localhost lookup there for IMAP or POP or whatever we implement, and you interact with this entirely through your email client. Why not a plugin, you ask? Because that would mean 10 different plugins for all the email clients that exist today and will exist over the next N years. Doing a localhost proxy means we only have to support, I guess, 3 OSs. Control messages, I said, are sent through the remailer network, but we can pass that off to the client to actually handle it. So there's a potential for using email itself as our interaction interface here. Now, this PIR protocol I've been talking about here, it's fairly simple, and we've chosen it over some of the more optimized ones simply because of its ease of auditability. Most programmers, particularly anybody who's familiar with the bitwise operation XOR, can understand this, and they sit down with it and spend an hour trying to get their heads around it, often less. Some of the other PIR protocol schemes, well, there are some of them that I don't understand. There's some of them that really good cryptographers I know don't understand. So There's a wide spectrum here, and we've chosen one that's secure, suitable for our purposes, and is easily understandable and implementable. It needs to be understood by the people that are actually going to be auditing this stuff, the academics that are going to be reviewing it, et cetera, so that the trusted authorities of our community here that the users are relying on to say whether these things are bad can actually find out if it's bad. And it also needs to be understandable for a programmer who may not be an anonymity expert or information theoreticist or so forth to sit down, read the spec that Nick's written up and go, okay, that's easy, I can implement that. But the way it works here is we have a fixed number of buckets in the system. The user chooses a number of the distributors out there, we call it L, to query, and he creates L-1 random bit strings where the bits, their length is equal to the number of buckets on the system. The remaining bit string is constructed such that the XOR of all of those bit strings together produces a bit string of all zeros with except for a 1, which is in the position of the bucket you're requesting. And then the distributors, each getting their bit string query with a bunch of 1s and zeros, take that mapping to their buckets, and they XOR all the 1 buckets together, and they return that XORed blob to the user. And the user then takes the responses, XORs it all together, and bam, there's their bucket. So now we can, as I mentioned before, we have these checksums in the hash rate tree to detect and see whether these have been tampered with. But assuming there's no tampering being done, this is what you end up with. So you've got things here. It should be a different color here, but this is the other 0th string, 1st string, 2nd string, etc., down to n, which we craft such that the results look like that. And then the same is the responses are processed the same way to give you the bucket you want. That's for you, Nick. Yay. And then the user's happy. He has a bucket. Talked about some of this already again. Right now, the way we are doing this is each user sends 1 request per day. Now, we're going to scale that up as we get more users. We can do pretty much as many requests per day to accommodate the most bandwidth-starved user in the system, as long as all users are behaving the same way. All the sizes are the same. All the responses are the same. Only thing that differs is some users may get more buckets than other users, but each user always gets the same number of buckets themselves every time. That's something that's pre-configured. I mentioned I mentioned that I would mention. Okay, so we have a management system in place for what happens if a bucket's full. If your buckets are full and messages are deferred. The buckets that you get include a summary message of what's going on with your account. Whether you have pending messages on the server, who they're from, what their subjects are, etc., so that you can send control messages and say, all right, delete all these things that say, dear friend, I'm lonely, because they're probably just spam. Or, for instance, you could get a list of all messages that really are good messages, but you really, really want to see number 20 in the queue, and you know it won't fit, so you can bump it up. We need to explore exactly how much flexibility we're going to give users with regard to controlling their messages through these things to make sure there aren't any additional anonymity attacks against them. But the facility exists to deal with a backlog of messages on your system, on the server. All right, now what happens if somebody tampers with your buckets? Tampers with the, what if a distributor, happy Nick? Nick has this hobby that I'll let him talk about later if he wants to. Yeah, we made a mistake. we were so concerned about protecting users from distributors that might do tagging on their responses that we built a system that was secure against that, but basically allows any single malicious distributor to denial service the entire system simply by responding with garbage instead of the answer to the PIR query. Because we can tell once the user actually XORs all of its stuff together and gets its bucket out, whether it's the real bucket or a naughty bucket. But we can't tell which of the unXORed bits, XOR blobs that came back was incorrect. I spent a while going down a rat hole of trying to figure out whether there was some sort of like pseudo checksum hash thing that could be performed over a set of data and then validated after that set of data was XORed, and it was a mess. I almost went insane. Maybe I am. It's not something that we can solve at the protocol level. Now, there are other PIR protocols out there that provide what's known in the literature as Byzantine robustness, that provide for dealing with cases where some servers may not respond correctly or may fail to respond at all, etc. Since our system allows you to make sure the server's alive before you actually query it, and it's a low latency, not time critical thing. The server failing in the middle of a query threat is not a big one, but the server tampering with something in order to denial of service the entire thing because you don't know who's doing the tampering and can't trust the results because somebody has tampered with it, and you don't know whether they're simply tampering because they want to screw with you or they're actually doing tagging attacks too, hoping you'll ignore this and just go forward, has become a problem. So we decided to take the solution to a higher layer in our protocol, or in our system here, because we're doing a system design. We're not doing a protocol design. And furthermore, I believe that for the implementability and analyzability standpoint, breaking out these things, oh god, 3 minutes, breaking out these things into discrete chunks so that people can analyze this thing, go, all right, what this is intended to do is correct, but it has this problem, but here's the fix, and what it's intended to do is correct, but it has this problem, but that's handled over here, and whoops, that's broken, let's tell Len he's an idiot. That's a lot better than presenting one big blob of protocol that does everything and you can't really disentangle it. So we've incorporated a new component to the system called a validator, which is essentially identical code-wise and operation-wise to a distributor, except that it does not actually perform any service in the normal course of things. It's run by the same operating entity that runs the collator and NIM server. So from a denial of service standpoint, they can already denial of service the entire network just by shutting off their systems. So we trust this not to denial of service the network. We don't trust it for anything else. And we extend the PIR protocol so that there's 2 queries to each server. One is the alpha set, which is the same, which is the good old PIR protocol set of bit strings I just talked about before. And then there's an identical ADA set, which doesn't request anything you're interested in personally. It doesn't request anything tied to you personally. But you send these to these 2 sets of bit strings to each distributor, randomized so that it's not always alpha or always ADA going first. And the distributors don't know which one's the real one, which one's the bad one. And if they tamper, they either have, if they tamper with one of them, not the other, they either have a 50-50 chance of succeeding with tampering with your stuff and screwing everything up, but that'll be detected at the end when the buckets don't match, or failing to actually screw your stuff up and screwing up the ADA set instead, which leads to them being detected. Or they can simply say we're going to screw everything up and be detected by tampering with both sets. I'm hoping that this functionality being in place means people won't try to do this kind of thing because they know they'll be caught. But yeah, Go back here to our unhappy walrus, and he's got a bucket that doesn't verify. The user can then take his data set, and he's cached the responses that the distributor sent to him for each data set. And he can send, one by one, the data set queries to the validator and compare the responses the validator gives to the ones that he got for each response he originally sent. And if there's a difference, then there's that distributor is likely the one that's the problem. And also bear in mind, this is more useful as a debugging tool for people that are designing this system and want other people to write independent implementations to make sure that they're actually interoperable, or to figure out that this one server here is having hardware problems and randomly flipping bits in its as through the network stack as things are going out. Then it is likely that this is going to be due to an attacker, but it's a real problem because even if it's not malice, we need to be able to debug these sorts of things. So, but jumping back here. The alpha, we can't just simply send the alpha set to the validator because then the validator is going to know what you're requesting. So we have this second set, and this unfortunately doubles our bandwidth, but we had some room there. So we send the data set up, and the validator returns its responses. The validator's responses should be identical to the distributor's responses because each distributor should return. You could send the same query to each distributor, and it should be identical for each distributor because they all have the same copy of the database. So there's still a concern the validator might try to frame innocent distributors. The validator and the collator and the NIM server are all in collusion, and they can try to convince users not to use these good, honest distributors, instead use other distributors that they're also running. Then we have a problem if they succeed. So we've got a couple of, I'm running out of time, but we've got a couple of methods in place to protect against that, but we're also, the key things here are the validator doesn't know which data set member was sent to which distributor, so if he's trying to frame a specific distributor, unless he is indeed a global adversary and can break TLS. I forgot to mention that the connections are all encrypted with TLS, but he generally doesn't know which data set member was sent to which distributor. So being able to consistently frame the same distributor over time is going to be hard. But I don't like having to add a new component to the system. So we're actively working on ways right now of distributing the validator's role across the normal distributors, so that that they do double duty on the validation side if needed. Now, there's a number of concerns with relation to that we're working on. This is active work. But one key observation, of course, is each distributor should get a different data set member than the first one it processed, or else it would just lie the same way. So where do we want to go from here? First, we'd like to get this thing built and used. Give me -1, please. All right, thanks. We want to make sure we get this thing built, used, and actually get the cypherpunk remailer system killed so that those reply block servers aren't in use anymore and aren't, Lucky Green, a cypherpunk that has been running remailers for quite a while, likes to say that running cypherpunk systems is tantamount to entrapment. I don't know if I'd quite say that, but it's close. Other things we'd like to do with this. Once we get that working, we'd like to see whether we can do forward message transmission through this and eliminate the cryptographic mix protocol approach altogether. And that takes away the kind of kludgy message control things to the mixes. Because mixes are fairly unreliable. One significant advantage to this over mixes as far as reliability is with a mix you need to predict that all the mixes in your chain are going to be operating during the length of time it's going to take a message to actually travel to the end. And since that time can be spread out over half an hour, mixes that might be up when you check initially might go down during that time period. With this system, you're querying everything simultaneously, and the likelihood of a future event affecting your query is less. Unfortunately, everywhere we rely on mixes, we still have that failure problem. And then the really nice goal would be to find a way to extend, see if it's possible to extend these techniques to low latency systems and keeping the usability and utility features of things like Tor bring the actual anonymity and security that they provide up a notch or two. My final comments are I'm out of time. So who wants to sneak in some questions? Yes?
What happens if a message is larger than the bucket size? You just get a partial message?
The question was, what happens if a given message is larger, won't fit in a bucket? We have a, what was the name we came up with for it?
We just split the messages.
Well, we split the messages, but there was some clever name, acronymed out to PIMPA or something like that. We split the message, and it either goes into the next bucket over, or it goes into the cache of messages waiting for you the next day. If that's happening to you on a regular basis, you should up your number of buckets. But the client, if it's the worst case where it won't fit in the bucket, it gets split, and there's no more buckets left to put it in, it's got to go in tomorrow's round, the client will keep the half message and tell you partial message, waiting for the rest of it. This is very much like how things are done in Mixminion with its reply, simply its reply blocks. We cribbed that idea from there. Other questions? Yes?
What if you send multiple bit streams from both your alpha and data set to each of the distributors and compare the data set results that you got? Like if you had duplicate, like send the same bit stream from your data set to other distributors, you can compare it that way.
That's true. I'd like to see we considered that. There are a number of reasons why we think that doesn't give us enough. There's trade-offs. Let's take that offline. We've thought of that. We think our way is better for a couple of reasons, particularly the ability to actually put it together and come to a bucket that has a hash that verifies out. Other questions? No? Okay, let's go to the reception.